In this problem, we'll be taking a look at a driven RLC circuit, which is a circuit that has a resistor, an inductor, a capacitor, and an alternating power source. These types of circuits are very useful in modern applications and are the basis of such things as AM radios. Along the way, we'll be confronting the notion of resonance and why it's an important, useful quantity. So let's go ahead and take a look at the problem statement. In this problem, we have a driven RLC circuit, and we're told a few things about how it behaves in response to different frequencies. So we know its capacitance, we know that we have a power source, which is oscillatory, an alternating power source. And we know that for a driving force in this power source of 5,000 radians per second, that the current has this particular form. And we're asked to find what does the current look like when the driving force is not 5,000 but 10,000 radians per second. So let's start by recalling a few facts about driven RLC circuits. And these circuits have one resistor, one inductor, one capacitor, and typically they have a driving source which is oscillatory. Oscillatory driving forces give nice behavior that's very useful for things like radios and things like that. So the way you would analyze such a circuit is similar to how you would analyze an LC circuit. You write down the circuit, you draw the circuit, write down the Kirchhoff's loop rule for the circuit by looking at all the voltages, and then that particular equation will give you a differential equation for the charge, which you can solve using differential equations, or you can just kind of guess the form and see if it works out. And what you'll find is an equation for the charge as a function of time. If you differentiate that charge as a function of time, you'll get the current as a function of time. And that'll tell you basically how the current behaves in response to different frequencies and different driving forces. I'm not going to carry that out here, but let me just go over the results. For driven RLC circuits, carrying that process out of analyzing Kirchhoff's loop rule, you'll find that the current as a function of time is given by some coefficient times an oscillatory term. That oscillatory term has the exact same frequency as the driving EMF, the driving power source. It may have a phase shift, so it may be a little off, shifted from the EMF, but it does have the same frequency. And then this max current, you can find its form, and that max current depends on it depends not only on the frequency that you're driving the circuit at, but also the circuit elements. So in particular, it depends on the EMF magnitude, it depends on the resistance of the resistor, and it also depends on the inductance, and it depends on the capacitance. So the form looks like this. This is all square rooted in the denominator. And then finally, we can also find a form for the phase shift, and that depends on the inductance, the capacitance, and the driving frequency. And that form looks like this. So what we're asked to find is the max current when the driving frequency equals 10,000. If we just look at this equation, we have an equation for the max current. Well, what do we have here? We have that the max EMF is 120 volts. We know the driving frequency is 10,000. We know the capacitance is 7 microfarads. We do not know the inductance, and we do not know the resistance. So those two terms are missing, and our approach here will be to use what we know about what happens at 5,000 radians per second to hopefully try to find out what R and L are. And once we know those, we can just plug them right in for omega d equals 10,000 and try to find out what the max current is there. So let me just say a little bit about what's happening at omega d equals 5,000. And what's very nice about this is if we just take a look at the current form, we see that it has the exact same form as a general form for current for an RLC circuit, but there's something specific about it. In fact, here we see that this is the same as that except phi equals 0. And so what that means is that the current and the voltage are exactly in line. In other words, when the voltage reaches a maximum, at that same instant, the current reaches a maximum. And this is only true for this particular frequency. In fact, for any RLC circuit, it's only true for one frequency. And the other frequencies, you're always going to have some phase shift. In other words, the voltage may reach its maximum at this instant, but it takes a little while longer for the current to get there. And then the voltage may reach its minimum at another instant, and it takes a little while longer for the current to get there. Or the current could be ahead of it. In any case, typically you're going to have a phase shift. In this case, you have zero phase shift. And when you have zero phase shift, that's known as resonance. And I'll say a little bit more about that, what that means in terms of the max current in a moment. But for now, let's just note that given the fact that for this particular frequency, voltage and current are in line, phi has to be 0. So let me just summarize that here. For omega d equals 5,000, phi equals 0, which is known as a resonant condition. And you can use that phi equals 0 for the frequency of 5,000 to try to find the inductance and the resistance using these three formulas. So go ahead and try that now. Use the fact that phi equals 0, the frequency is 5,000, and try to find the numbers for the resistance and the inductance, and we'll take a look in a moment. So setting phi equal to 0, we'll get the tangent of 0 equals this quantity. The tangent of 0 is 0, so you'll end up with 0 equals the right-hand side here. R cancels, so you finally get that 0 equals omega d times L minus 1 over omega d times the capacitance. We know the capacitance. We know the frequency here is 5,000, so solving this for L, you find that L equals 5.7 millihenries. Okay, so that gives us the inductance. We still need to find the resistance. But before I do the mathematics for that, let's just note a couple more things here. We have that this particular quantity, which is the numerator of this tan phi here, equals 0. And that quantity is the same as right over here. So in fact, if you look at this expression for I max, when we have something in the denominator which is a positive quantity plus a positive quantity, we can't change R in the circuit because that's fixed. However, we can choose the omega d. And if we choose it such that this quantity is 0, the denominator is as small as possible because this can only be as small as 0. And if the denominator is as small as possible, I max is as large as possible. So in particular, for this particular frequency of 5,000 radians per second, I max is as large as possible. In other words, we've driven this circuit to get the biggest current possible with that frequency. And so what that kind of looks like is this. It would look like if we chose a frequency that is not equal to 5,000 versus a frequency that is equal to 5,000. And if I just plot the current as a function of time, then in the first case, if you're not on resonance, this I max is not as big. So you kind of get something that looks like this. It's oscillatory still, and this I max, which is the height of the peak here, is some particular number. Now, when you drive it at 5,000, you've made this I max as big as possible, so you have very large oscillations, and this amplitude here is as large as possible. And so what we find here is that, in fact, for 5,000, the I max is 2 amps. But if you choose any other frequency, the I max will be less than 2 amps. I'll also note that if you look at this formula, if I just kind of write it, I'm just going to kind of invert that formula. It can also be written like this. Omega d squared equals 1 over LC. And this you may recognize as the natural frequency for an LC circuit. So in other words, if I just had a capacitor and an inductor, and I put some charge in the capacitor and then hooked it all up and let it run, the current will go back and forth with this particular frequency. Now, this kind of makes sense in terms of resonance because what we're doing here is we have something that has a natural frequency of 5,000. If I just put some charge in the capacitor and let it run, it would go back and forth at 5,000 radians per second. What I'm doing here is adding a force that not only lets it go back and forth at 5,000 radians per second, but I'm driving it at that same frequency. And so the analogy here is kind of imagine you have somebody, the common analogy is you have somebody in a swing, and if you just let the swing go, it goes back and forth at a particular frequency. If you, at the same rate as which this thing is going back and forth, if you push it at the very end at 5,000, it'll get higher and higher. And so as long as you kick the system at the same frequency at which it naturally oscillates, you'll have resonance. In other words, you can get the current as big as possible here. However, if you push it at a different frequency, you may not get the most bang for your buck in a sense. You may not have this thing go as high as possible. So here what we're doing is we're kicking the system at the same frequency at which it naturally oscillates. And that is a resonant condition. That's when the I max is maximized and when you get the most current for the particular voltage you're putting into the system. All right, so going through the mathematics here, we have that finally solving for the resistance, we know that the I max at 5,000 is 2. We know epsilon m is 120, and we know that this term is 0. So if I just write that, then we get that I max equals epsilon m over, this term goes away, so you have r squared square rooted, which is r, and then plugging in 120 for epsilon m, 2 for I max, you're going to get r equals 60 ohms. Okay, so we've found what we needed. We have the inductance, we have the resistance, and now we can all plug it in for omega d equals 10,000. So now if I plug in all these values, 120, 60, plug in 10,000 for the frequency, 5.7 millihenries here, 7 microfarads there, and then carrying this all out, you'll find that for a frequency of 10,000 radians per second, you get a max current which is 1.62 amps. Does this make sense? It does, because we found out that at the resonant frequency, the I max is 2 amps. So any other frequency we choose, which is not on resonance, should have a lower max current. So this is kind of similar to this situation. And this is exactly what happens in AM radios. When you have an AM radio, you're basically tuning some part of the circuit. I don't remember if you tune the inductance or the capacitance, but you're changing one of those values. And when there's a frequency of a wave coming in at a particular frequency, let's say it's 5,000 radians per second, if you choose LNC right, then you can choose it correctly to get the max current coming through. And then your radio realizes that it's on resonance, and you can actually hear that station coming in. So I'm going to go ahead and stop there, and we'll take a look at the summary. In this problem, we analyzed a driven RLC circuit. We first recognized that the current and the EMF had the same time dependence with no phase shift for a driven frequency of 5,000, which told us that phi equals 0. And using phi equals 0, we found the inductance and the resistance. And then finally, we found the max current for oscillations at a different driving frequency using these values that we found. So the key in this problem was to recognize that for a driving frequency of 5,000 radians per second, the current and the voltage were in phase, and that told us that phi equals 0. We proceeded from there. If you have any comments or questions, please leave them on the link accompanying the video, and we'll see you next time.